Hi. So you would have thought by the end of the entire semester, I would have gotten better at these making video things. Absolutely did not work out. Absolutely not. I totally screwed the videos up this week. The best part was when I recorded the entire thing with it muted, with no audio whatsoever. So I'm starting over. We're going to talk about concurrency. We got 2 videos. I'm going to keep them nice and short and sweet. First one is going to be definitions of the different important terms that you're going to need when you start talking about concurrency. We talk about why this problem exists and what's hard about solving that problem, how we're going to be successful at solving it. Then the second video is purely going to be, here's the different flavors of how we solve it. Here are the ways that we're going to deal with it. Here is the way you'd say, well, I'm going to use this way versus that way, whatever have you. These are all generally going to be good jumping off points for doing a deeper dive into concurrency, but we didn't really have enough time in this semester to dive too deeply into it. If you're interested in this, I definitely say that Chapter 12 is a good introduction, and what we're going to be doing in these 2 videos is a good introduction. The assignment is a good introduction. The elevator assignment from last year, the one that I previously used for homework 6, is a fun, good assignment. If you want to take that one, please let me know. I'll give you the skeleton code, whatever have you. And with all of that said, let's talk about concurrency. So concurrency is a thing. So for 2 things to be concurrent, we have an A and a B. If A starts before B and A ends after B starts. Those are the 2 things that are necessary to actually have 2 things be concurrent. So if A had started here and B started after A, but it started after A had ended, there's no concurrency. They're not doing anything at the same time. Even though the topic of this chapter is concurrency, right? We got all the way to chapter 12 in this entire book on computer systems. We've been doing concurrency since the beginning of 361. It pops up basically everywhere in the stuff that we've been doing. The main issue is that it usually doesn't matter from our perspective because the operating system is providing us with isolation. So the operating system, remember, this is one of those really, really core concepts of 361. If you want to internalize what it means to be good at computer systems and systems programming, understand the operating system exists to provide isolation to multiple running processes. Isolation is good because it allows us to program without worrying about everything else that's going on around us. We don't have to coordinate with other processes to have our memory layouts. We just have virtual memory, so we don't worry about that. Context switching means that I run my program with my stack pointer and my instruction pointer and my general purpose registers. I get ripped off by the operating system. I get put right back on, and everything about my current status gets saved and restored without me having to worry about it. And so I don't have to worry about saving my own registers. I don't have to keep track of where I am. None of this stuff is necessary in normal operation for 2 different processes that aren't trying to share resources because the operating system is doing its isolation job. That is incredibly, incredibly important in what a modern operating system provides to programs. We just program as if we were the only process there and we can do whatever the heck we want for as long as we want. That's all fantastic. Isolation is a good thing that the operating system provides for us to make it easy to program and not trip on each other's code or text or memory or registers or whatever it is that could possibly happen there. However, concurrency gives us 2 really, really powerful capabilities. So the 2 main things that concurrency is going to provide us as advantages is that we can do parallel computation, and we can use multiple different resources at the same time for different running programs. So with parallel computation, if we have more than one CPU, we can run more than one thread at the same time. They can run actually in parallel, boom, 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 boom. Because if we remember, when it comes to concurrency on one CPU, we're not actually running both of these at the same exact time. We're actually hopping back and forth between them as, say, if we had 2 different processes running on one CPU, we're actually just running the first one a little, running the second one a little. First one a little, second one a little. And when we have multiple CPUs, we can actually run more than one process at the same time. And if those 2 processes don't have anything to do with each other, they're completely isolated, they don't have to worry about tripping over each other, right? This processor has one virtual memory, one page table entry loaded up. This other processor has a different process, different page table, different virtual memory, different everything, and they just do their own job as if they were completely independent of each other. The other huge benefit that we get out of concurrency is that we can use multiple resources at the same time. The biggest example of this is a page fault to pull something in from disk. When you pull something in from, say, a spinning disk, it's going to take tens of milliseconds, which is incredibly long when we're dealing with processors that do billions of operations per second. So what we want to do is say, we're going to stop this one thing because we're waiting on a different resource, and then run somebody else in the meantime, and then run the other one over again. By splitting different jobs up that are isolated or maybe not isolated into their own concrete tasks with their own threads of control, we can get more stuff done because we're able to use all of our resources as efficiently as we possibly can. If we only could run one process at a time, we would have to run those CPU instructions, wait for a really, really long time while the disk spins around, and then we start running again. All of that extra time can be used to interleave different processes. And if we're doing isolation correctly, that's usually pretty easy. We don't usually have to do too much there. But a lot of the times when we want to take advantage of parallel computation, when we want to get some job done using more than one CPU, using more than one process, whatever have you, they're going to need to have some idea of shared information that they work off of. Maybe it's simply as much as a queue where this one gets this job, that one gets that job, this one gets this job, that one gets that job. But there's always going to be some coordination layer where something has to be coordinated between all of them. They can't just willy-nilly pick from a list because something could go wrong. So that going wrong is the topic of the next section of this video. So when we're running two different programs at the same time that are working on the same task, you're almost always going to have some concept of some shared resource that both of them want to be able to touch at any one given point in time. And on top of that, sometimes they are going to be doing those operations, those individual CPU instructions, in a way that they leave that shared information in an inconsistent state. And this is where the isolation that we were relying on before no longer applies. If we can't isolate them, if they have to share some resource, they're going to have to be smart about how they share it, because it's very easy to screw things up and end up in a situation where you corrupt the memory, end up in a situation where bad things happen, even though you didn't have a seg fault or you didn't have a test fail or whatever have you. It's really, really nasty. So let's look at a relatively simple example. This is kind of a canonical example here, where we're going to talk about withdrawing and depositing money to a bank account. And you could imagine that that withdrawal looks like a little bit like this.
A few moments later.
Something like that. My SQL is rusty, so maybe that's not the right thing, but the basic idea applies. And then likewise, we have deposit, which is going to be the same exact thing. Concurrency becomes a problem when you can leave a system in an inconsistent state while you are working on something. Another really important concept that I want to cover here is interleaving. So when you interleave different instructions, an operating system can interleave instructions however they want, as long as they are valid to be run as the next instruction. So if I was running two different programs that were running withdrawal and deposit here, then if I said that the first instruction was this one, the plus equal or minus equal is this one, and then the last query is this one, anything that puts all three of those in the correct order, like first instruction, second instruction, third instruction, first, second, third, any sort of like this is legal, 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 anything you could possibly think of where those three things are in that order, like this, whatever have you, are completely valid for the operating system to actually do. When they schedule those two processes, it's completely possible that they could be run in any interleaving, where I run this one, that one, that one, this one, that one, this one, that, whatever have you. Now that becomes really important because in this situation, there are interleavings that will leave the system in an incorrect state. For instance, if I ran this one, and then I ran 3, 4, 5, then I ran this one, what would end up happening is I run the withdrawal. So I pull the balance out, say my balance is 100. I decrement my balance by say 10, goes down to 90. And then when we get to this third instruction, we ask the database for that balance. We still get 100 because nothing has been pushed back into the database yet. We still get 100. We add to the balance. We add 10 to the balance. We get 110. We save 110 in the balance here. And then we go back to this other instruction. And here, nothing else has happened. It was using a local variable balance. It was running everything as it is supposed to. it's going to take that value 90 and store it back into your balance. So even though you deposited $10 and withdrew $10, you end up with a balance of 90. That's an incorrect, inconsistent state. What we fundamentally want is to say, no one else can touch balances. So we want to say, okay, others can touch balances. And the same thing goes down here, where we say, everybody else that wants to touch a balance, don't do anything. And then we say, okay, we're done messing with the balance. Somebody else can mess with it. And if we have a system that allows us to do this, then yeah, somebody might start running this and they might start running this. But then if the operating system decided, oh, hey, I want to switch over to this run of deposit, we get to that line, we say, oh, well, somebody else has the ability to touch balances right now. I'm not going to go past this line until I run this instruction, and then this one can be run next. That's fundamentally what we want to do. Most of the synchronization that you'll be doing at just a basic level is going to look exactly like this. This creates what's called mutual exclusion, also known as mutex. And we're going to implement this with the ability to call lock and unlock on a specific mutex. So one other important part to this is that if I had a really big banking system where thousands of people were trying to make withdrawals and deposits at any one point in time, if I said no one can touch balances, period, then I would have a very slow system when it got really busy, because I'd have to say, okay, I can do this one, then I can do this one, then I can do this one. Whereas if I'm touching Chris's balance and I'm touching Joyce's balance, then there's no interaction between them. They're perfectly isolated. They're not going to have side effects with each other. It would probably be better for me to say no one can touch Chris's balance. And then, okay, other people can touch Chris's balance. And no one can touch Joyce's balance. Otherwise, and then when you're done, you say everybody can touch. You can make things correct, but there's a very big difference between correct and optimal or high performance, because you can always see, okay, how much do I need to protect and how much do I actually not need to protect? So what these end up looking like in the real world, in C, the no one else can touch is going to be a pthread mutex lock, and you give it the address of a locked element. So you have to initialize that element. And so maybe it can be the balance lock, like it would be in here, or maybe it can be the balance lock for account X, in which case only one person can touch account X. Then maybe if you want to transfer from one account to another account, maybe you would lock X and then you would lock Y if you needed to go from one account to another. There's lots of different ways that you'd be designing this. And there's a lot of just practice and art and seeing examples that goes into being able to come up with the right way to lock things. There's a bunch of rules. It's beyond the scope of what we're going to go over in class this semester, this week. But the main benefit we're getting here is we're saying the operating system is only going to schedule things based on whether they have these locks or not. And once they have them, they can do whatever they want. They can run. They're not going to get stopped. Like they could get stopped for something else, but whatever else that is something else that's isolated from them that isn't going to impact their operation. Once they come back, they're going to finish what they're going to do. They're going to call pthread mutex unlock, and then they move on with their life. If both of these withdrawal deposit were using that same pthread mutex, then they would not have any sort of interleaving problem, because they were protecting what's called the critical section. So I don't know what the definition the book uses for this, but critical section to me is basically the area of code that has to be run atomically with respect to anything else that is also a critical section. So what this means is I can not stop halfway through a critical section and let some other critical section run at the same time. I can stop halfway through and let some unrelated code run, but I cannot under any circumstances run like I did here with that example. Run the first instruction and second instruction of critical section 1, swap over to critical section 2, run a few of its instructions, and then swap back over. That's where you end up with these dangerous things. And if you saw those drawings in the book where they have like those matrices of dots or whatever, and they say, okay, well, you can go in this way in this program and that way in that program, and this region is the critical section. right? What they're basically saying is if you interleave in such a way that you go through that dangerous area, you're interleaving in a way that will probably cause incorrect results. I'm not going to test you on those diagrams, that they're a little hard to understand. Like once you really have a good understanding of what's going on, it's like, oh, you can go back to it and be like, oh yeah, that makes sense. That's pretty cool. The core thing here is really interleavings happen when two different pieces of code rely on a shared resource that they both have access to, that they can both update. You need to make sure that the interleavings that happen do not leave that shared storage medium in an inconsistent state or cause any sort of inconsistent operation to happen. The main way that we do this is by protecting those critical sections such that they can only run when they are safely allowed to do so that they don't interleave with each other. That's what I've got for you today, and I'll see you in one more video.